Welcome everyone. This technical webinar is about cable ampacity calculations using the finite element method. Myself and Dr. Edson Fernandez are here, who will be your presenters. This webinar will run for 1.5 hours. As I was saying, these calculations we're quite familiar with. They're very useful for cable ampacity is to use the finite element method. We've been doing these calculations in depth for a number of years. So Edson, are you gonna
Yeah,
run
yeah, I
through
will.
housekeeping and stuff
Yes.
briefly?
Let me go through it. Okay. Welcome everyone. This is a presentation on FEM, which is hosted by ELEK Software. As Jason pointed out, we have been doing this for a couple of years, and we've been presenting many papers around this topic. Our presenter for today will be Mr. Jason Patrick. He's the technical director at ELEK Software. And we developed electrical power system analysis software. Jason has extensive experience in high voltage design, power system analysis roles, and he's also a professional software developer. He leads a multidisciplinary team of developers, PhD researchers, and cloud architects, and we develop a multitude of softwares for power system analysis.
What
Now,
about
this
yourself, Edson? Edson, what about yourself? Can you introduce yourself?
ah
What's your
okay.
expertise? Yep.
I'm the lead technical researcher at ELEK Software. I specialize myself in cable rating calculations, power system analysis, and earthing grid analysis. Yeah, something short about me. Yeah, so now the topic FEM, very hot topic these days. Always IEC has been used. IEC 60287 has been a standard which was used benchmark for quite a lot of years. Then came through TB 880, which again benchmark many of the calculations of IEC. But the problem with IECs was that it's always limited to certain, like for example, a single backfill, no complex convection scenarios. So all these shortfalls of IEC, we will be discussing it today. We will be seeing how FEM can help you to do all these effects, and also we'll be talking about the latest developments in FEM, which is soil tryout, multiple casings, horizontal directional drilling, multiple circuits in a duct. And also we will see how the convection models between air and soil is affecting your cable rating. So I'll hand it over to Jason, and Jason will start the presentation. Thank you.
Okay, Edson, so just briefly, what are the limitations of the IEC analytical methods? When should we
The
use FEM?
Yeah, the IEC methods are basically the analytical methods are restricting you to certain cable types, restricting you to certain cable formations, certain configurations. For example, you can have only one duct. The sizes of the duct are restricted between 25 to about 100 mm. There is no
Uh-huh.
air convection model between the soil and the air. So lots of limitations. There's only
Yeah, I
one
forgot about
backfill.
that one. I forgot about that one that the duct size has a
Yeah.
restriction,
And
right?
right size addition, the duct materials also a restriction. You could have only 5 or 6 materials like PVC, PE,
Yeah.
concrete, all those materials. But in FEM, you can do any type of duct, any size, any duct material, etc.
Hmm. Okay.
Yeah. Sorry, I just forgot to tell you the rules. Just to introduce the rules. So we prefer cameras to be on. Microphones would be off, but you can type your questions in the chat. We will take it up at the end of the session. There will be a certificate that we will give you that will be sent to you. There will be a form which you will have to fill out, and once you do that, we will send you the certificate of attendance. Yeah, Jason, it's
Yeah.
ready for you now.
Thanks, Edson. Okay, yeah. So if you don't mind, turn your cameras on. We'd love to see you. Please type in the chat where you're dialing in from. We'd love to know. Um, and let's get started. So who is ELEK Software? Just very briefly, we are a software company headquartered in Sydney, Australia.
Uh,
Yeah.
Jason, I'm not seeing the second presentation. Yes, I'm seeing the first screen itself.
Uh-huh. Okay.
Yeah, now it's okay. Now it's good. Yeah.
No, no. Can you see what?
Yeah,
Sorry.
yeah.
You can
Yeah, we can
see
see now.
my you can see
Yeah.
my second slide?
Yes.
Okay. Yeah, so we are headquartered in Sydney, Australia. That's where our head office is, but we're also a distributed team. Um, so we have three main software products. So ELEK Cable Pro Web for low voltage electrical design, ELEK SafeGrid Earthing software for earthing system modeling and analysis, and ELEK Cable High Voltage software for cable ampacity calculations. We have a lot of customers globally in many different countries. We develop the software, we do the research and development, we build the software, we support the software, and we support the customers. So there's a sort of a recent photo of some of our team in Sydney. In this presentation, I'm going to talk about the finite element method and how it applies to accurate cable ampacity calculations. This is an updated version, the latest version based on the latest advancements that we have been working on and that we can share with you. So I'll talk about IEC 60287, which everyone knows about, those current rating calculations and their limitations. Edston, you can see my slide correctly now, right?
Yep.
Yep.
Yeah.
I'll talk
Yeah.
about the fundamentals of FEM for cable ampacity and the advantages of that. I'll talk about how to combine IEC with FEM. I'll talk about meshing, how that's fundamental to FEM, boundary conditions and sheet bonding, how we deal with that. Cable modeling, guidance with an example. Are we going to do that as an example briefly, Edston?
Yeah, we can do a brief one. Yes, we can.
Uh-huh. So just show a few cable models, or
Yeah.
maybe one or two. IEC versus FEM current ratings. This is very important to understand that you're going to get different results, and I'll explain that and why. Throughout the presentation, I may ask Edson to be involved. He's an expert in these calculations, and so it'll make it more interesting. It won't be just my perspective. FEM for complex installations. So we'll talk about where FEM must be used, and there are certain complex installations where only FEM can be used. Soil drying around cables, how you deal with that in the finite element method. We have a methodology for that. When to use IEC or FEM, air convection modeling inside the ducts, and there'll be a couple of calculation examples. So it looks like multiple casings, horizontal directional drilling, you've got to use FEM. Cables in ducts in backfill with a road surface, you've got to use FEM because you've got multiple zones of different soil thermal resistivity. I'll draw some conclusions and recommendations, and then we'll have a Q&A session. So this session will run for 1.5 hours approximately. Well, it will run the full time, and there'll probably be lots of questions which we can answer at the end. But I think as we go, Edston is usually and some of our team like Michael are very good at answering your questions as we go. So type them in the chat, and we will answer them. So ELEK Cable HV software, just quickly, these are the calculations being shown using ELEK Cable HV software, which is accurate and validated software for cable current rating calculations. It's been around for quite a long time, around since 2010, the first development. We've been building upon this software and these calculations for a long time. This software is very flexible, has a lot of capabilities, as you can see along the top, has a lot of different installation methods that it supports, and lots of different modules that it includes. There's really not many scenarios at all that it can't handle. It's suitable for any AC voltage, so from low voltage, including DC, any cable types, up to any AC voltage, including HVDC calculations as well. It does comply with IEC 60287, which is the main authority for cable rating calculations. And it also obviously can perform FEM calculations. It can perform current rating calculations for custom cables under your specific installation conditions. So it's not like using simple lookup tables. But generally, those lookup tables are based on IEC 60287 calculations anyway. It's fully validated with CIGRE Technical Brochure 880. We have full matching results to 11 decimal places for all of the case studies, but it has much more capabilities. You can actually register for a free trial at elek.com. You can start using the software within a few minutes. It doesn't actually require download. IEC 60287 current rating calculations. This is a series of standards. I believe there are 9 parts to the standards, lots of different updates to all of those parts. It's a broad standard, right, Edston? There's lots of different
Yeah,
parts, lots of
9 parts of it.
ambiguities. What's it like dealing with IEC 60287?
It's a long way to bring it into a calculation method because it's very the document is not very clear.
Mm,
There are many speculations. That's why TB880 had to be brought out to clear all those speculations so that everyone is on the same platform.
mm.
But it has nine parts to it, all very important parts, all very almost descriptive parts to it. It's difficult to understand, but reading it along with TB880 makes it much more simpler now.
But IEC 60287 calculations are generally, mm, a lot of them are a little bit simpler. Simple methods, for example, cable crossings, like we needed to
Yes,
extend those calculations. They're
yes, many of the
simplistic.
calculations. Yes,
Mhm.
many of the calculations had to be extended because they deal with one or two circuits only at the max. So,
Mm-hmm.
for example, transients can do only one circuit at a time. Cable crossings can do only a cable and a steam pipe at a time.
Mm-hmm.
So there are many restrictions. Yeah.
Many limitations. They're really relatively quite simple, but the fundamentals are really important and still good. So this standard series continues to be widely adopted because it is adapted to common, still modern cable types and typical installation methods. It's regarded as reasonably accurate. It has been validated in the field, uh, and therefore it's regarded as needing to reliable current ratings for new and existing cable circuits. It's still used because it ensures consistency and comparability between different bidders, providers, and suppliers or other stakeholders. Like we discussed, the calculations are somewhat complicated to implement and very ambiguous in parts. You need to spend a lot of time understanding them, actually. Validation of current ratings with IEC 60287. So there was a relatively recent technical brochure from CIGRE TB 880, which provided, which um, sort of cleared up the ambiguities, some of the ambiguities in IEC 60287. That was the intention, and so provides 11 benchmarked examples with 17 calculations, 49 guidance points. It was prepared by experts from around the world who were able to agree on what's the right process for performing these calculations. Because the problem is that all of these experts were performing the calculations to IEC 60287, and they were all getting different answers because they're ambiguous, the methods. So TB880 provides a verification procedure to validate existing calculation tools, and we've used it for that. We have full matching results, which you can, I think all of the case studies are included with our software, and you can see the results are published on our website. So in general, it's this brochure is in accordance with IEC standards, and it's in line with the current best practices. There are also armor loss calculations. Accurate armor loss calculations are not provided in IEC 60287. Of course, there are armor loss assumptions, calculations in that standard, but they are regarded by the industry as very conservative and inaccurate. So particularly around three-core armored cables. What is it? There's an assumption of 1.5 multiplying factor of
Yes.
the
So
conductor losses or something, right?
yes. So what happens is the magnetic field that is created by a cable, it is assumed to be contained completely by the armor. So to make that adjustment, IEC has suggested a factor of 1.5 to be multiplied with the conductor resistance, um, so that we make some adjustments for that. But what TB90, it says that the sheath will also be very effective in shielding the magnetic capabilities of the cable.
Mm-hmm.
So the armor doesn't need to be that much of a problem, and they have removed the 1.5 factor, and then there's a new calculation method which takes into the magnetic permeability of the armor and doing the calculations, which will actually give us a much reduced lambda 2, that is the loss factor of the armor,
I
and
think
so we'll have an increased current rating.
I think what I've seen is, and correct me if I'm wrong, but the sheath losses are increased,
Yes,
and the armor losses are significantly decreased, and
significantly.
it's an overall
Yes,
reduction in losses
yes,
in the cable, in the three-core
correct,
cable, and
correct.
resulting in typically around a 10% increase in cable ampacity,
Yeah,
right?
that's what we have seen. Yes,
Yeah, yeah,
yes.
yeah. Okay, so yeah, so we have implemented this method, these guidelines in for three-core armored cables, which is also very important. The finite element methods, I think so. We've implemented these calculations for a long time, for more than 5 years. We've had this, and but very recently, so May this year, was it released in? Okay, it was
Yeah,
released
may,
in May
yeah,
this year.
yes.
There was a technical brochure on this, how to perform cable ampacity calculations using FEM, which is a good thing. It's taken quite a long time to come about. We've been providing these calculations to industry for much longer. We also make it very fast and easy, as you'll see. 6 case studies are provided, 67 guidance points are prepared. We have done lots of comparisons with this new brochure, and we have good matching results. Small differences, but with these numerical calculations, it can be quite different in their setups. It depends on the calculation engines that you're using. There's lots and lots of calculations. I think if you do this traditionally, like as the way as these, it seems like the way that these experts have done it on the working groups, it's a very manual process. There can be lots of openings for differences in calculations. I mean, which FEM package you're using, how you set up the meshing, the environment, so many. It introduces many more variables than the traditional IC calcs. And so, and it's a very time-consuming process to do this using traditional FEM software and methods. It can take days, weeks, and a lot of training. So we use similar calculation engines, but we've fully automated. We've integrated it with the IEC calculations, and we fully automate the cable modeling and the modeling of the environment, etc. So that you can do it just like a simple IEC calc, but you're doing FEM. So we have matching results with this brochure. So what are the problems with IEC 60287 calculations, and why would you use FEM? So the IEC calculations make assumptions in the external thermal resistance calculation that are often inaccurate, inflexible, and limiting. So there are thermal resistances. It's a thermal network that we use to calculate the cable ampacity based on IEC. And it's particularly the external thermal resistance calculation, T4 calculation, which it's really the most complicated calculation. It depends. It's modeling an equivalent thermal resistance of the external environment to the cable. So that's where FEM really shines. So the analytical equations of IEC 60287 are limited to the assumptions. So the T4 calcs in IEC are limited to the assumptions that the ground surface, for buried cables, is isothermal, which means that's ideal. When in reality, it's not. Isothermal means that it's at constant temperature across its boundary, and also that there is no convection between the ground surface and the air above. That's ignored. So again, very ideal. Now, when you're dealing with shallow buried cables, this is very much not the case, especially. And also that it assumes the cable surface is isothermal, so point 0.2 there, when it's not. So isothermal means constant temperature. But when you have cables that are in close proximity, touching cables, like as you can imagine, the temperature around the perimeter of the cable, it's not the same. It's not constant. It varies a lot, depending because of the mutual heating, the heat field from the other cables, not just the other cables, but also the environment. And the IEC calculations also use the superposition theorem for mutual heating, which is very simplistic. If you recall back to your studies, the superposition is a simple way of adding up, in this case, heat sources. It's which is okay for cables that are separated widely, but when they're in close proximity, the superposition theorem is very inaccurate. So there are recent case studies on, not even that recent, but it's been well known for some time that the IEC 60287 calculations have these limitations and can result in inaccurate cable ampacity calculations because of these assumptions. There was a relatively recent study, R&D project by National Grid in the United Kingdom, that advised that this assumption of isothermal ground surface results in overrating. So, in other words, the IEC 60287 calculations are optimistic about cable ampacity. You'll get higher cable ampacity or assumed higher cable ampacity when you use these calculations compared with the finite element method. They use the finite element method. Now, that's especially true for shallow buried cables, including those installed in surface troughs. So the findings of this report were that they don't want anyone to use IEC calcs for the T4 calc for the external thermal resistance, in particular for cables that are buried at 1 meter or shallower. So what are the advantages of FEM? I've already sort of explained, but FEM can deal with any cable installation configuration. So you can see some examples here. I think we can do much more than this as well, but like zones of different soil thermal resistivity, you simply can't do this with IEC 60287 analytical methods. There's no way to do it. You've got a mix of different cable types, touching cables, different zones of thermal resistivity, troughs, ducts that are air-filled, ducts that are filled with water, ducts that are filled with solid, any combinations. FEM can deal with this. So your exact installation conditions can be modeled. This leads to better accuracy. So it's much more flexible. For example, FEM can model multiple zones of varying soil thermal resistivity. That's what the boxes here, rectangles here of different color. Those have different thermal resistivity, so they represent backfills compared to the native soil. So you can have multiple layers. Other advantages of FEM are the heat transfer between the ground and the air is modeled. So the ground surface is not assumed to be ideal or isothermal. The IEC standard assumes that no heat transfer occurs between the ground surface and the air above, known as the isothermal assumption. FEM allows the convection of heat generated by the buried cables, which flows into the ambient air, to be considered. So it's an input. We take the input of soil temperature and ambient air temperature. Is that correct, Edston?
Yes, yes, soil and air ambient temperatures, and we would also require to calculate the heat transfer coefficients also. Either the software can do it, or you can enter the values also.
Yeah, yeah. But it's much better if we just do that for the user, right?
Yes.
And
Yeah, yeah, yeah.
it's an iterative. That's an iterative process, right? To be accurate,
Yes,
yeah.
yes.
And
Because the heat conversion coefficient changes with temperature,
yeah,
so it has to be iterative within itself.
yeah, yeah, yeah. So the ground surface is not a constant temperature, right? In FEM.
No,
Yeah,
no, it
yeah.
changes.
Mhm. Okay, so you can see, I think we have an input for air velocity as well, right? And that will change the rating. Yeah.
Yes,
Oh,
yes,
yep. hmm because it changes the ground surface condition temperature. Yeah.
yes. Ground surface temperatures. Yes,
Or effectively the heat transfer coefficient. Is that correct?
yes, yes.
hmm And I think we also have an isothermal setting in FEM, which we can also show. So it allows you to compare
Yeah,
IEC with FEM.
FEM. Yes.
Okay. Further advantages of FEM. So I talked about the mutual heating. So this superposition theorem is shown on the left. This is quite an old image, but this and there's the equation there. And this is a very simple equation for considering mutual heating. So it just considers the losses of the cable, each of the cable, and their separation distance, the distance d, and the reflection with the ground surface, right? It's done. Uh, and d dash pk. This is very simplistic. It doesn't work well for touching cables when you want to consider mutual heating. So mutual heating effects for cables in groups are more accurate using FEM. With FEM, the mutual heat flux, influence, and disturbance. So the heat flux is disturbed when cables are in close proximity. So it's a good idea to combine the IEC calculations with FEM. And that's what we've done for. So the electrical losses and the thermal resistances in the cable are based on IEC, and then we performed the FEM calcs based on for the external thermal environment, including from the cable surface, including ducts and backfills, etc., or the environment. And then there is the general equation for cable ampacity. Now, a lot of these uh, inputs are temperature dependent and need to be iterated upon. So it's an iterative calculation, and the FEM is iterative in itself. So yeah, it's an iterative FEM calculation that you need to perform. There is a hierarchy. So the FEM model, organizes the objects in the environment. Now we model everything in the cable. So from the conductor. So if you see on the right-hand side, this is what's called a mesh plot. That's where we divide. Now the finite element method is based on dividing the environments, including the cables, into elements, and that's an automatic process. Now, what we need to create those elements as smaller when we have a boundary condition or when the material changes. So from the conductor to the screen to the insulation, at those boundaries, we need to use a tighter mesh or a smaller mesh for better accuracy. And then as we go into extend into the environment, the meshes can get larger. And where the nodes meet, those triangles meet, those are called nodes. And the method involves calculating the temperature at every single node, solving for temperature at every single node. So, and then you're also allocating losses to the electrical components in the cable. So the heat source in this model is the conductor, but also any metallic objects. Also, the insulation is a heat source due to dielectric losses. So all the heat sources are modeled, and then we calculate the temperatures. And then from the temperatures, we can solve for ampacity based on temperature limits that are need to be adhered to with the cable. So it's a large system that we uh, organize into hierarchy. We mesh into using meshing, FEM meshing, and then we solve. Meshing of objects refers to discretization. Yeah, did someone listen? No?
Yeah, the meshing is very important because if we see this image, the edges should be meshed very fine. Otherwise, results will be inaccurate. So whenever there is a change in thermal resistance or when there's a different material, we always mesh that edge very fine. But the other part, like the environment, if you see on the left hand side or within the conductor, if you could see, the mesh is very coarse. So finer meshes are good, but it'll take much more time in getting a solution.
So there's a balance, right? And we have a lot of experience in that, and we've done a lot of experiments over the years, and we have or we automatically do that in
Yes,
our software for the user. But there's also air convection inside this duct, typically that also needs to be modeled, right?
yes, yes.
So
This is
Mhm.
Yeah, this is one of the disadvantages of IEC method,
Mm.
where they would consider some analytical models for air convection, and they're
Yeah,
fixed constants. So that's why you cannot change the material of the duct in the IEC method.
yeah. So FEM, so the meshing is performed individually on each component, each layer in the cable and its environment. I'm not sure if we're going to talk about the broader environment, but there is a boundary to that. Finer meshes result in accurate solutions, but they compromise the speed of calculations, as Edston said. Shown in the image here is a double armored, that's a HVDC cable, right? Single core
Yeah.
HVDC cable with double armor, which is quite complicated to model, but yeah, so we need to mesh all of the layers. Boundary conditions. Okay, yeah. So boundary conditions should be sufficiently large. So you'll see in the bottom right hand corner, this is a mesh of an environment that spreads from 150 meters minus 150 meters to 150 meters. So it's 300 meters wide. It's 100 and
Jason,
yep.
Jason, we're not seeing the next screen. I mean the next. Yeah, now okay. Now it's come up.
Is there a
Yep.
little bit delay? Okay.
Yeah.
Okay. Um, yeah, so the the boundary conditions we've got we need to set up a larger environment and we model the cable systems within that environment, within the boundary. We automatically set up the boundary and the boundary conditions in our software. But the boundaries should be sufficiently large, but not too large, but such that there's no heat transfer across the three boundaries. So that's a little bit tricky to do, but we do that in our software. And the top boundary is a different boundary condition, so that the surface, the ground surface, should consider, heat transfer effects, particularly from air convection, as you can see from the diagram. And around the edges, those are finely meshed again for the same reason that we have potentially a change in well, wherever a boundary ends, we need to apply a fine mesh. I think these settings you can adjust in our software, but we've set them up automatically. Sheath bonding, this is very important, has a big effect on cable ampacity. So we would advise to use the IEC calculation method so that you can deal with all of the sheath bonding arrangements. And I think it doesn't deal with everything, but there are still some extensions required. But in general, solid bonding will when you need to model that, if that's the bonding that you're going to use, it can result in 20 to 40% reduction in cable ampacity. Single point bonding, widely used, cross bonding. We have different presentations on this topic, and this we have some very good content on this on our website. I highly recommend that you search sheet bonding calculations and go to the ELEK website. There's lots of practical advice there about this. Our software can deal with all different bonding arrangements. The diagrams are shown on the right-hand side here, solid, single point, and cross bonding. There are some different variations. She's circulating current for solid bonding. It can, so when you solidly bond the metallic objects, so bonding at both ends of the cable circuit, you can see significant sheath circulating currents. I think in our software, we've recently updated the results displayed. So maybe we'll see that today in what Edston is showing. We can see like all of
Yeah.
the circulating currents in all of the cables, right? On a per cable basis.
Yeah, we will try to show it. Yeah.
Okay, cool. And the voltages as well
Yep.
on the sheath, for example. So when you solidly bond the cable, now this is a 400 kV cable with solid bonding. It's not going to happen in reality, but we can see the cable ampacity limited to 850 amps with a current on the sheath of over 500 amps. This is just an example. So the losses in the sheath are significant, which reduces the cable ampacity. This is just a fundamental understanding for you. Cable modeling, a very important process, critical process in any cable ampacity calculations, including FEM. As I've shown you, so you need to model the cable from manufacturer data sheets, and they can be of varying complexity, but you should obtain those data sheets from manufacturer. And each of the objects within the cable will have both thermal and the metallic objects will also have electrical properties. Those need to be modeled. You can use the IEC standards or CIGRE guides for those material properties. Those are embedded in our software. And you can follow the guidance of CIGRE when you're setting up the models of the cables, which is what we do. You should avoid combining layers of different materials in the cable. You should model every single layer separately. In our software, we would model custom layers and assign properties to those custom layers. But you're modeling the cross section of the cable exactly in terms of thicknesses, dimensions, material properties, number of wires. What else, Edston? Lay length. What else?
Lay length of wires, yes. The overlap of wires of tapes.
Mm-hmm.
Um, yeah, and all the material property like thermal resistance is very important for
Mm-hmm.
all the layers.
Makes a big difference, right? What you assume. Um,
Yeah, it makes a large difference, especially for example, we had an example that we did for a customer. What he complained that the cable was not giving him the results that he required. But when we looked at the cable model, instead of using XLPE at a higher voltage, he was using the XLPE at a lower voltage. So
mm-hmm.
XLPEs are two types. He was using a lower voltage XLPE, and that's what was not able to get his results. So yeah,
Uh-huh.
so minor changes, big difference. Yeah, that's what we
Very,
have seen
very,
from.
very
Very
big
big difference.
difference, right? Just
Yeah.
one value of say thermal resistance or I guess that would have had an effect on dielectric losses, right? Was that the main impact there with that customer for the different
Sorry,
XLPE?
Jason?
I guess that the main effect there would have also been dielectric losses when you're choosing a
Yes,
different
dielectric
XLPE.
losses were very high. Dielectric
Uh-huh.
losses were very high. It went up to I think 20 or 30 watts per meter, and the cable was heating up pretty quickly at very low current. So that's why they weren't able to get
Yeah,
a
yeah.
result.
So set your cable model up well initially. So I don't think we should model a cable from scratch. maybe we'll just we're already halfway through and we have a lot of
Yeah,
content to go. So let's just quickly show the cable model editor and a couple of different cables, I think. If
yeah, yeah,
that's
yeah,
okay,
yes,
Edson.
yeah.
Just
I can share my
just
screen.
in under 5 minutes.
Yeah, can you share my screen, just?
Um, yeah, you can.
Yeah. Okay. So yeah, so this is the environment for cable high voltage software. I'll just concentrate on cable modeling. So we have a library of almost 1,200 cables in this, from different voltage levels, from 1 kilovolt to around 400 kilovolts, and each of them have different types of cables like corrugated sheet, smooth sheet, etc. You have the long list of HVDC cables, which is 320 and 525 kV. Each of them have different types of cables and different voltage levels in
So
them. Some of aluminum, copper.
why don't we look at just a complicated HV single core
Yeah,
cable
so
and then a three core cable, maybe a submarine cable or something.
Yeah, so so this is a very complicated HVDC cable, double armored cable, with a copper conductor. So
Mm.
it's a 320 kV cable. We can define the properties of the materials in each of the tabs that we see here.
So
So
on the
if
left
you
hand
look at
side, we're setting up the layers, right?
Yes, we are setting up the layers one by one, and then we are entering their respective properties in the tab. So if I can look at the armor layer, this is the armor layer one. So it is steel wires touching. There are all the parameters of the armor wires entered. Um, there's a second armor here for the same cable. Again, the same properties with different diameters have been entered. And finally, we have the outer covering, which is a jacket, which is a polypropylene yarn. So we have a list of materials that you can use. We could also have even custom materials in this. For example, there's a long list of custom materials to choose from to meet your requirements. So we can use any of the custom materials, or you can have your own custom material. So this is one simple example of a DC cable. I can show you another example of a three-core pipe type cable again, which we have in our database. Um,
Probably. Do we have a just three core submarine? Okay, pipe type.
yeah, I can give you
This wouldn't be widely used in APAC pipe type cables.
yeah.
It's
So
more in
we
the
can look at
US.
this cable, which is Yeah, so this is under 30 kilovolt multi-core cable. Um,
That's an
and
AC
this
cable,
cable
right?
has a yeah, it's an AC cable. It has a sheath around each of the core, and each sheath has a jacket around them too. So that's why this cable is special. So it's individually sheathed and individually jacketed too. So here also you could have lots of custom layers in between. For example, between the conductor and the screen, you have a custom layer which is a tape, which is it's a fabric material. So you could model all your materials in this. It has an armor and an armor bedding, which is common to all the three cores.
Can we have a look at the
If you look,
conductor and the insulation?
yeah, the conductor here is a round standard conductor. It's not Millikan's round standard conductor. DC resistance is picked up automatically, and it's 630 squared.
Hmm.
Um,
What about the insulation?
the armor is important here because the armor material properties which we have shown here is used for TB908 also. So when TB908 is used, these properties come into play. So that they are important to be defined.
So this is a three core armored cable, and so the accurate armor loss calculations from TB908 are implemented if you select them in the
Yes,
settings, right? Yeah.
yes,
Yep.
yes,
What
yes,
about the
yes.
insulation layer?
The insulation is an XLP insulation,
Hmm.
unfilled XLP, because
Yep.
about 30 kilovolt we are using this, and then we have a long list again of insulations which you can use for your cable.
Yep.
One important thing here, Jason, I want to highlight is
Mm.
about sorry no, about the DC cable. Just
Mm.
give me a second to bring that up. Um, Yeah, the DC cable is important here because we have one extra constraint in DC cable, which is the temperature drop across the insulation. So I
Yeah.
think So this temperature drop restricts your cable ratings. And in our software, we have methods to calculate it. If you know the stress of the cable or insulation stress, then we can calculate the temperature drop across insulation, and then we
Okay,
can stick
okay.
your
Um,
cable ratings.
so in a non-HVDC cable, we saw that there is this maximum operating temperature, right? This needs to be this is 70 degrees in this case. This needs to be set for every cable type, right? An insulation layer has a temperature limit, right? But with HVDC, there is also a temperature drop across the limit across the insulation, right? And that
Yeah,
corresponds to an electric field limit of the insulation, right? So that's what you're saying. Uh,
yeah,
so it's another
yes,
constraint for HVDC. Cool. Yeah.
yes, yeah,
Okay. I
right,
think we'll continue with the
yeah.
presentation. Yeah. Just let me know when you can see my screen. It's done.
Not yet. It's coming up, but a bit of time, I think.
It's a long way to go, I think, all the way from
Yeah.
Ireland.
Uh,
Have
yeah,
you got
it's
my
good
screen?
now.
Okay.
Yeah, yeah.
You got the next slide. This is a very interesting slide.
We are seeing cable modeling example.
Uh-huh. No, you should see comparison with IEC and FEM.
Yeah, now.
Hmm. Is this our
Yeah.
latest plot? I think there's another one.
There's another one. Yes, that's another one.
Uh,
Yeah. But this is comparatively good enough. This one, shallow
uh-huh.
depths, is good. Yeah.
Uh-huh. Uh-huh. Okay, so
Yeah.
this is a this is an interesting plot, this one. So as I explained earlier, FEM is more accurate, but it doesn't mean you get higher cable ampacity when you do more accurate calculations, unfortunately. So in general, the current rating that you'll get from an FEM calc can be significantly lower, uh, particularly for touching cables or cables that are buried in shallow depths. So in other words, if you doing IEC calcs on your cables and they're important to you, you should take care because uh, the FEM method, and this is widely known in the industry. And oh, my laptop is running low on charge. Okay, this is widely known in the industry that the IEC calcs can be optimistic, and so if these circuits are important to your networks, you really should use an FEM calc as opposed to a simple IEC calc. So FEM can be used for complex installations, as you can see here, like lots of different backfill types, any cable arrangements. We do the meshing, we calculate the temperatures, etc. There is a setting for isothermal and non-isothermal ground surfaces, just so you could compare with IEC. When you set FEM to use isothermal, you'll get similar results to IEC, pure IEC calcs, but not necessarily that close because we're still using proper mutual heating calcs with FEM. The FM can be used for installations like this, where you have a large pipe and lots of ducts inside the pipe. This is for like a crossing of a river or something like that, or a roadway. FEM can deal with this. I think we can deal with any number of ducts inside pipes, right, Edston? Now we can do multiple
Yes, that is.
circuits inside the duct that which we're going to explain and show you in an example. There's no limitation, right?
Yes. So this is basically multiple casings,
Mm-hmm.
and also
Mm-hmm.
multiple circuits in a duct.
Mm-hmm.
Yeah, that's where the pipe type cables and river crossings come into play.
Mm-hmm.
Yeah, very
Mm-hmm.
complex air convection models have to be modeled inside these casings.
Mm-hmm. I think Michael, who's also part of our team on the call, is well versed in these calcs as well as
Yeah.
Edston. Okay. Multiple circuit calculations. FEM does really well at this. The mutual heating, when you have like a duct bank on the right-hand side, with touching cables, the the mutual heating gets it's very, very important. It causes a large reduction in cable ampacity when you have duct banks. We've been modeling in the recent weeks these trenches for solar farms. We have a lot of circuits, and some of these vendors and or construction companies are not actually even modeling their trenches, and they're seeing a lot of overheating of cable circuits in their trenches because they haven't even considered the extent of the mutual heating, which is very, very significant. So modeling of HV cables at wind farm landfall. This is an interesting, useful application, particularly of FEM. So if you're dealing with cables that are directionally drilled, in particular in the bottom right-hand corner, cable circuits that are directional drilling involve directional drilling. So where you're drilling and then pulling cables into a pipe in ducts, you must use FEM calcs. Here's another scenario where the IEC calcs are actually wrong. There's an assumption where when you have multiple circuits in a backfill, the assumption of the IEC is what it's done. So I think it assumes that all of the cable circuits have the same losses. So I think the situation is when the two circuits are carrying different currents, right? Then the mutual
Yeah.
heating is wrong for IEC. Is that right?
Yes. Yes. Because IEC considers all circuits to be in the center of the backfill.
Uh-huh.
That's one large problem for IEC. Yeah. When the difference of current ratings between the cables, then we have an overestimation by IEC.
Overestimation. Yeah. Yeah. So this actually results in an overestimation of temperature. So in this case, it's not optimistic when you've got a backfill like this, when multiple circuits are carrying different currents, you run into this problem. And as Edston said, there's an assumption that the heat sources are all at the center of the backfill. And when you have a backfill of an odd shape, then like this shape here, this assumption goes very wrong. So FEM calcs have a very wide application, particularly for solar farms, as I've already mentioned, where you can have lots of circuits in a backfill. There can be multiple backfills. There can be situations where DC cables are in close proximity to AC cables, even medium voltage cable circuits. So lots of different cable types, different backfills, multiple backfills, different environments. Lots of mutual heating happening. Also, different load factors uh, and different cable temperature limits, etc. You need to use FEM for this. Multiple circuits inside a duct. We've recently worked on this. This came about mostly from the solar industry, where they are pulling lots of DC circuits into the same duct. And the IEC calcs don't deal with this directly. So again, you must use an FEM calc and to do these calculations. And the as you would imagine, the the convection inside an air-filled duct with multiple circuits is very important. And we've done some studies. I'm not sure if it's shown in this presentation, but even when you move the cable circuits around in the duct, if you assume they were in the middle or separated in the duct, which is physically impossible, but if you did make that assumption, you'll get a very different result. And this just proves that the modeling is correct. In reality, cables duct filled with air, the cables are going to be sitting in the bottom of the duct. They may be lumped together, or they will be lumped together, and all of this heat interaction will affect the cable ampacity. So I think with our FEM calc, I'm not sure if we're going to show an example. Are we going to show an example of this, Edson?
Yeah, we can show an example. Yes. Yeah.
Do you want to do that now, just quickly?
Uh,
Yeah.
just just a bit more later, Jason. I'm just doing the
Okay.
calculation. I
Yep.
don't want everyone to be
Sounds good.
waiting. Yeah.
Sounds good.
Yeah.
Yeah, we'll show that. Soil drying around the cables. Now, this is also very important, but it's a bit different in FEM. So in IEC, we use this two-zone method. We've done a webinar on soil dryout again. Before, we may do it again. Soil drying is really quite complicated. It is approximated using this two-zone method according to the IEC standard. Now, that means that you have a soil thermal resistivity when the soil is moist and a soil thermal resistivity when it's dry. And we say that when a soil zone or area reaches a critical temperature or goes above a critical temperature, it will dry out. The dry soil has a higher soil thermal resistivity. Now, that needs to be considered in your model. And there's an IEC way of doing it, and we have implemented a similar method in FEM. I'm not sure if we're going to show that, but it's very important to consider, and it results in a significant decrease in cable ampacity when you consider soil drying. And if you don't, you could run into overheating issues in the field. So
Yeah.
yeah,
The IEC,
yeah,
the IEC method, what it does is it is a two-zone model, right?
yeah.
So you have one zone of the moist soil, and then the other zone is a dry soil, and then the boundary is isothermal there too.
Uh-huh.
So, so, so it's like a step curve that you get between moist soil and dry soil thermal resistivities.
Yeah, yeah.
But in FEM, I think it's also in the coming slides. You will see that there is a slight slope in it. Probably it's there in the coming slides that you can explain that.
Uh-huh, uh-huh. Yeah, so there are limitations, as Edson alluded to. There are actually very significant limitations to soil drying calculations in IEC, and we've had to extend those methods. I mean, it was you could really only apply the IEC calcs with soil drying to a single isolated cable circuit, which is really impractical, right? In reality, cable installations almost always involve multiple buried circuits. You couldn't use the IEC calc with soil drying for that. So we needed to extend the IEC calc. We've done that. We have advanced soil drying calculation capabilities in our software. And also you couldn't apply it to non-unity load factor. You had to assume 100% load factor. This is also impractical and conservative in reality, especially for, renewable energy installations. And you can only apply soil dryout to direct buried cables. Now, what happens when you have cables that are installed in a thermal backfill, which is stable against soil dryout, but the soil outside of the backfill is not? Well, you can't use the direct IEC method for this. You have to do some advanced calculations, and you also should do that. Have that capability in FEM. It's a little bit different in FEM though, right, Eston? Uh, Here it is
Yeah,
here. Yeah, you might want to
yeah,
explain.
yeah. Your screen is not seen till now. We are waiting for the
Uh,
screen. A bit of
okay,
lag, I think.
okay,
Yeah. Um, Let me assume. Just wait for it to come now.
okay. So consider soil drying in FEM calculations. You can't see?
Yeah, yeah, this one. Yeah, this is what we are talking about. So in IEC, if we look at, we would see that is a step plot between dry. So this is a moist zone of one Kelvin meter per watt, and the dry zone is 2.5 Kelvin meter per watt.
Yeah.
So in this example, this is an example from TB963. So the critical temperature is 50 degrees. So at 50 degrees, we assume that the soil thermal resistance changes from 1 to 2.5. So IEC consider this like a step change, and because of that, any discontinuous will not be considered there. So you have either 1 or you have 2.5. But in FEM, we don't do that. We consider a smooth transition between dry and moist soil. And because of that, it's more realistic than the others. And this can also mean that your backfill can be thermally very stable. You don't have to apply dry out for backfill, but for the surrounding soils, you can apply a dry out, and that's
So
what that is shown here in this plot.
So we in our software we assume that the backfill is thermally stable, so it's not susceptible to soil drying. But
Yes,
the
yes,
surrounding environment
yes,
is not, and we apply this function curve. So
yes,
we do the meshing, and then we
yes,
calculate all of the temperatures, the soil temperatures, and
yes,
if and then based on that, we apply a
yes,
soil thermal resistivity
yes.
to that mesh, is it right?
To that node, to
To
the
that
node.
node, to the node, yeah.
Yeah, to that node. So when you do that, it becomes iterative in itself, because when you
Mm-hmm.
apply a value of thermal associated temperature changes, so we'll have to achieve a convergence in that. That's why salt tryout calculations are time consuming with FEM.
Yeah, it's fully iterative, right? So we have to then go
Yeah, fully
back on the
iterative. Yes,
calculations again, recalculate all the temperatures again, and then reapply the
correct,
function, and then again and again and again until we have convergence.
correct,
That's why
correct.
that's what we're talking
Yeah,
about when we say iterative calculations. Now, on the left-hand side, we've got with soil dryer and without soil dryer. Um, I think what this is, you would expect kind of higher temperatures on the right as opposed to the left, but what we're seeing on the left is a reduction in cable ampacity, a strong limit on we can't run the cables as hot when the soil is going to dry out. I think have we applied some soil dry out limitation there or no?
no,
It's just simply
it's
applied,
only it's only I'm glad you
and
just soil.
we have the same cable conductor temperature limit. So the
Yes,
cable can't reach a high temperature
yeah,
when you modeling the soil drying out.
yeah.
So this is an interesting topic. We often get asked, when should I use IEC as opposed to FEM? And as we've seen, like, why would you use it if if the cable ampacity is going to be calculated as lower? Now that depends on your perspective, right? Sometimes if you're a contractor or a consultant, perhaps you want to get as much cable ampacity out of your cables as possible in terms of the model. But if you're an owner of these assets and you're worried about longevity, well, you might want to be more conservative, or I would say, FEM is more accurate, right? But you're not really strictly mandated to use FEM. I would also say, however, that's again down to your own engineering judgment. Um, So there are cases here, so where we would say, what's the recommendation? So simple direct buried cable, IEC for simple configurations, but if you have complicated arrangements, multiple backfills, and with soil drying, you will have to use FEM. So there are situations where you just have to use FEM due to the limitations of IEC. But if you can model using IEC or FEM, well, if the cables are deeply buried, you'll get close results. But if they're not, FEM should be used when the cables are shallow or for complex mutual heating. When cables are in ducts, I mean, FEM is going to give better results when you need to consider armor losses, etc. You'll need to just incorporate the TB908 calculations in both your IEC and FEM calcs. Steel pipes, I don't think there's any difference. Multiple cables in duct bank. FEM better models mutual heating and electromagnetic interactions for complex arrangements. So again, complex installations, you will have to use FEM. It's highly recommended that you do, but don't expect better results, higher cable ampacity. So yeah, I highly recommend that you probably take a screenshot of this slide for your future reference. Air convection model inside ducts. This is very important. I mean, if you're modeling ducts, you have to accurately model the convection inside the duct. It actually depends on the cable position in the cable, the arrangement of the cables in the ducts. Now, this is not captured in IEC calcs, but it is calculated in FEM. So FEM is very flexible. You can, consider the an accurate size of the duct, the materials, and also the positions of the cables, the number of cables in the ducts, the cable dimensions, and the losses of which are the heat source. We can see that the cable position affects the airflow, and this is modeled in FEM. It's not well modeled in IEC. Multiple casing calculations, FEM. You have to use FEM for this. You simply can't use simple analytical IEC calcs to model cables that are in ducts that are being pulled in pipes for horizontal directional drilling applications. Edston, can you see this slide for multiple
Yeah, now.
casings?
Yeah, now.
Was there a delay?
Yeah, there's always a delay.
Of how long?
Uh,
A
about
few
30
seconds.
seconds.
30
Yeah.
seconds.
Yeah.
Okay. Okay. So hopefully we're answering your questions. Hopefully there's not a delay in those. Type your questions in the chat. Um,
Yeah.
okay, I'm moving on to verification of casings with CIGRE FEM. Can you see that slide? Um,
Mm,
so,
no, we are seeing multiple casing calculations.
so in multiple casing calculations, just let me know when this slide has changed because I have changed it. But
Yeah.
multiple casing calculations are really, they're at the top end of complexity when it comes to cable ampacity calcs.
We are seeing the
Uh,
next one, Jason.
yeah, because you've got, cables in ducts where convection's involved, and then you've got pipes, lots of complexity in the heat flow. You need to, when you do these calcs, you'll need to validate them. We have validated our calcs for multiple casings with this case study by CIGRE. Do you want to say anything about this, Edson? I think this is a
Yeah,
relatively simple, actually,
it's a relatively
installation.
simple thing, but the problem here is for IEC, the assumption is cables to be in the center of the duct, which is never a possibility. And IEC doesn't
Mm.
deal with filled ducts too. So FEM can do all
Uh-huh.
those things. So here, FEM in
Yeah, IEC
reality,
doesn't deal with field ducts.
yeah. So yeah, in FEM we can do solid filling, water filling, etc. And you can place the cables exactly where they are, like it to be in the belly of the duct. So yeah,
Often,
so this is a good validation that we can do.
often cables in direction drilling applications, I mean, they're grout filled, right? They're pumpable,
Yeah, they're grout filled normally. Yes.
they pump
Yeah, the second
materials into
example.
these.
Yeah, the
Mm,
example on the right is where the casing as well as the ducts are filled with grout, but
mm.
there's an empty duct also on the right which is not filled.
Yeah, they won't
So
fill
the
it.
air
They won't
movement in
fill
that
it.
has to be modeled.
So you
Yeah.
can't do this using a simple calculation.
No,
You have to use FEM because
we have
some
to
of the
use the
ducts are
calculation.
grout filled, some are air filled, and it leads
Yes.
to complexity.
Yeah. Yeah.
Yeah. So verification of FEM calcs. Look, it's important to know that your FEM calcs are correct, right? There's a
Yeah.
there's a lot of variability in these calculations. It takes a lot of time to set them up. If you do it manually yourself in an FEM package, we've done it for a long time. I would strongly not recommend it. It's extremely painful. We had someone dedicated to this for around a year, and we saw what it was like. But it's important that unfortunately everyone does these calculations a little bit differently because there's a lot of variability, and therefore there's been another very recent technical brochure from CIGRE which has helped. But we already had matching results um, uh, with their brochures, the examples in their brochures. These are relatively simple examples. You can get, but it's a very good baseline. But you can get much more complicated, deal with much more complicated installations with FEM. So yeah, so in terms of our calculations, I mean, we know they're accurate, and we have the proof of that. So, uh, did you see the TB963 verification it's done?
Yeah, we saw one of them.
Okay, now this I'm
Yeah,
showing
now
the
the second
second
one.
one. Now the second
And
one.
yeah, now the second one is there.
And now we are going to show some calculation examples. That's the time now.
Yeah,
Um,
yeah.
so if you would like to share your screen
Yeah, I'll share my screen. Yep.
and just explain what you're going to show us, and we
Okay,
can we
so
can we can chat about it, and I may ask some questions or something.
yeah, so for convenience, I've pre-calculated the results, so we don't
You've,
have to
you've,
wait.
okay,
Now,
but how long
FEM
did it
is
take to set this up? Like, not
okay.
long to.
Setting this up, yeah, setting this up is another story. For example, to show you a simple to create a simple setup here, for example, in FEM. I can just show that quickly. So, for example, I'm doing a three phase system. I want to, for example, I want to put it in ducts, and I want to assign a casing to it also. So, in our software, it's pretty straightforward to do. You can go to ducts, or let me make it in a triangular fashion. I can go to a duct and add ducts to it. So now ducts are added to this circuit. I
We
could change
recently
the
added we recently
diameter.
added these automatic ducts encasement to
Yes,
FEM, right? And it's much
yes,
easier.
it's much easier now. So now we have added a duct to the cables. Now, if we want to add an empty duct, we can go ahead and um,
So we can put this. I'm not sure why you're using triangular, but we can
yeah,
put
just because
this.
I want to create the casings that we showed them.
Oh, okay.
So I can add another duct. I can make it an empty duct. So this is an empty duct. I can drag and drop it wherever I want. I could change the dimension. Let me keep it as a simple, like small duct, for example. Let me add another duct there. Let me increase the sizing because this is um, going to be a casing for me.
I think it's a
I
good
can
idea
drop the
to
case.
make that duct the same dimensions as the.
Yeah, yeah, yeah. We can do that. We can just 140. Sorry, 140 and 119.4.
So that's the
Yeah,
inner and outer diameters. Yeah.
yeah. And then we can move this into position.
There's a bit of a delay when we're running Zoom, I think. My computer is running
Yeah,
slow
Zoom,
on
Zoom,
Zoom.
Zoom takes a lot of time to run. Yeah, so we could adjust this one, and then we could fill all these ducts with, um, for example, now it's air filled and PVC ducts, but we could go ahead and fill all these. Yeah, Zoom is taking its own sweet time, I think. Yeah.
Yeah. I mean, the beauty of FPM here is that um, you can't model empty ducts in IEC, right?
Yes, yes. No empty
And
ducts,
they
no
and
empty
they
backfill.
and they affect the heat fields, right?
Yes, yes. Especially if the other ducts are solid filled, and if your empty duct is air filled, then the air movement in that duct would create a cooling effect for the other cables.
Mm-hmm.
So you have to model empty ducts or even empty backfills also. We have seen they have an effect on the cables. So even empty backfills you have to create. So if you want to have a backfill, for example, we have seen example where there is a small layer of asphalt on top of the cable. For example, a concrete layer or something like an asphalt on top. So you
On
can
the
model
ground.
that,
Yeah.
and then you can run your calculations. Yeah.
Okay,
So
so
this is how
maybe
we set up everything, and then we define all the ground surface conditions, etc. So just to show you an example of multiple circuits in a duct. So this is like I think four circuits, two circuits, and two circuits. in a duct. So this is for a solar farm that we did very recently. The customer wanted to know what is the temperatures that the cables will see because of this arrangement. So we did it on the FEM. We could see the temperature plots on the contours, seeing where the contours fall. We could also see the mesh plots. So this is how the mesh plot looks like for this type of an arrangement. So if you see all the edges are finely meshed, and as we go out of the soil, the meshes become very coarse. So this is a large area that we have meshed. So I've just zoomed it, but this is a very large area. So this is one example I want to show you. The another example I want to show you is the TB963 case. This is exact the TB963 case that we have modeled here. We've got very similar results. We should always understand that FEM depends on the calculation engine which you are using. So if you use our software or if you use a different software, the results might be a bit different. Like you might get 615 for something, 625 for something. That's because the FEM engines are different, solvers are different. So yeah, so we have very close results to FEM. That's what Jason showed you earlier. This is with an extra layer of asphalt on top of it. You cannot do it in FEM. Sorry, you cannot do it in IEC methods. You can do only it in FEM. And here, if you see here, the cables are placed at the center of the duct. So that's what the mesh plot also shows you. If I can zoom in a bit. Yeah, you can zoom in and look at your cables, how they are placed. So if you see here, the cables are placed in the center of the duct. So this was done to study how IEC compares with FEM. So that's what this was done to study. That's why we kept the cable in the center of the duct. But there's also a case study in TB963.
It's then,
There was another case study.
are we, yeah, okay. Are we going in terms of time? I think we are at 1 hour and
Yeah,
20, 1 hour and 20 minutes. Am I correct?
20 minutes. Yeah, I think we don't have
Okay.
many questions. So yeah, so just
We
this
don't have,
example too.
mhm.
We don't have any questions to answer.
Let's
We'll take
just,
some.
we'll take
Yeah,
some
yeah,
extra questions. There may be some
yeah,
extra
yeah.
questions.
Okay,
So
okay, fine.
just a
So
1 or 2
let
more
me.
minutes.
Yeah, yeah. I think I'm okay with this. I think this is an
Ah,
example again, which
ah,
which in TB963, but with bentonite filling.
mm,
So here the filling is bentonite, and because of that, we would have a higher rating than cables in air. So yeah, so
okay.
this is also one example that we have done. Yeah.
Okay.
So I can look up for a few questions and ask you, Jason.
So
Uh,
no, I think you should reshare your screen instead. Just keep the
okay.
software open. Maybe someone has some questions about something they want us to show.
Okay. I think
Yeah.
there is one question that is asked about loaded cables in service. I think that's what I showed in the first one. So these are loaded cables in service. So the user knows what the current rating of the cables are. They want to find what is going to be the temperature on the cables.
So
So that's what. So this
there's
is
two
one line.
settings, right? So
Yes, there are two settings.
you can either set a temperature limit for the cable or you can give it a fixed loaded
Yes.
current. Is that what they're talking about?
Yes, yes. So in FEM, so yeah, so there are two. I mean, you could apply limits practically anywhere. So if you look at our cable modeling settings here, you could apply temperature limits on the conductor, the sheath, or the jacket, or the duct, or the pipe also. So anywhere you can apply a temperature limit, and our software will calculate according to that limits. So this is one example, which I mean, sorry, this is an example which I can show you.
1 second, Edston. So I've placed a link in the chat where you can request a certificate of attendance. If you click that link, if you fill out the form, you will receive a certificate of attendance.
Yeah, thank you, Jason. So one thing to show here is, for example, another challenge that we had is a customer had two circuits pretty close to each other, carrying heavy current. They were single point bonded. So because of that, we would see that there are standing voltage calculations done for all the cables, individual cables. Now, the question that the user asked is, what happens if circuit 2 goes out of service? If I want to service it, now, the problem when that happens is you would have induced voltage from circuit 1 onto circuit 2. So he wanted to study what would be those induced voltages and whether it is safe to work on those cables. So we have this feature here, which is in service or out of service. So now it is 90 degree at about 25 degrees Celsius is the ambient. So if I make it out of service, so I'm taking circuit 2 out of service. So now if you see, the temperature is around 49. So instead of 25, it's almost 14 degrees or sorry, 24 degrees higher than expected. That's because the first circuit is heating up the second circuit. Also, you would see there is a standing voltage on the cables. Although very small, you have a standing voltage on the cables. So this is one important thing that you can do with our software. Study the effect of out of service circuits, and you can see all the single point bonded standing voltages per cable. We can display them for you. Yeah, I think that was one question that I wanted to answer, Jason.
Okay. Um, so we're open to questions. We've got 5 minutes left. If you are there any open questions? Um,
One
maybe.
question is, uh,
Mhm.
let me just read for 3D FEM. Uh, how do we deal with 3D FEM? Have you plans to apply 3D FEM?
Yeah, one day. Yep. Yep.
Yeah, yeah. 3D FEM is
Uh,
a bit involved. Yeah,
maybe. Um, have you been answering the questions? Maybe Michael. Just unmute Michael. Does he have any any things that he thinks that we should
yeah.
Yeah,
show?
thank you, Jason.
Hi, Michael.
Yeah, hi. Yeah, I see the questions for the 3D FEM. I
Mm-hmm.
mean, yeah, I think that's actually a good advice because like with the 3D FEM, we can definitely model the whole system more
Mm-hmm.
accurately. I mean,
Mm-hmm.
the only issue is just about the computing power because for most like the desktop computer that we are currently using, even for the 2D FEM, it can take much time for the calculation and convergence. So for 3D FEM, I don't think there is any like technical like limits for that. We can definitely start the program for that. The only concern is just about like as I mentioned, the computing resources. The FEM compared with the 3D FEM compared with the 2D can definitely requires more computing power. And if we are going to plan for this project, we need to take care of this and consider it more
Yeah,
carefully.
yeah. So with 3D FEM, I mean, in theory, you can better model mutual heating, longitudinal heat
Yeah.
transfer along the cables. Potentially, yeah. It's a project of ours that we uh
Mm,
will undertake.
yeah.
So once again, there's a certificate link in the chat for everyone to use. Any other interesting questions? Edston,
One question was about soil temperature measurements. How you can
mm,
estimate soil temperature at certain depths.
mm,
Yeah, I mean, we have a
um,
calculator. I was telling about them that we have a calculator. This is a calculator that can calculate temperature at various depths depending on your mean annual temperature,
yeah.
etc.
So
for different soil.
often, we assume a soil ambient temperature from the standards. It can be, it's usually quite conservative, and it does have a big impact on the cable ampacity. So getting that right can be is a good idea. But obviously, your client needs to accept it, needs to be reasonable. There is a theory that, so particularly for deep buried cables, it's quite unreasonable to assume that the soil ambient temperature is so high from the standards. And there's a theory that says that soil temperature will approach average annual air temperature with depth. So the deeper you go, the average annual temperature, which is often much lower than these assumed 25 degrees or 30 degrees soil temperatures. If you go deep and you look at the average temperature for over the whole year, the average temperature for the region might be 12 degrees. And so you can apply this model, and that's what Edson is showing on the screen. As you go deeper, soil temperature will reduce. And we have used this on projects and it's been accepted. This theory is relevant and can save you a great deal on your cable costs. and it's more realistic. So yeah. Any other questions?
Ah, I
We
can
good.
check it.
I think we're good.
Yeah, I think we are good, Jason. Yep.
If you would, thank you everyone for attending this technical webinar. We'll have more of these in the coming weeks. Yep, very good to see you, Brian. Long-time customer. And look, if you do have any questions, please send them to support@elek.com. We'll be happy to answer them. But most importantly, we really look forward to seeing you on the next technical webinar. Thanks everyone for your input. Thank you to my team, and we'll see you again soon.
Thank you.
Thanks. Thanks everyone. Bye bye.